Welcome, guys. Welcome to Upskill Club AI for EPD series, session 4. Today's in the last session, we learned the basics of game theory, how AI agents are impacted by it. Today, we're going to go a little deeper in terms of understanding what is in reinforcement learning, predominantly focusing on understanding its basics and making it relatable to us by understanding a couple of real world examples. In a nutshell, reinforcement learning is basically very simple, as the diagram here tries to conveys. There is an agent, there is an environment. Agent takes an action based upon some parameters. Either they are rewarded or not rewarded. If they are rewarded, they take that as a note. That's it. As simple as that. Real world example that we have used is DALI. That is this image real or not? Correct. And reward can be somebody verifying manually. That is when it gets triggered. You can play around with that, but this is in a nutshell. An agent will do something in an environment, it will get or may not get an reward. This is reinforcement learning in a nutshell. So I guess today's session is over. Cool. No, we have other things to learn. Let's go inside. Okay. So, in technical definition, reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment to maximize cumulative rewards. In a nutshell, how many reward it will get, it tries to maximize it. That is what RL or reinforcement learning is. A real world example would be, think of training a dog. How do we train a dog? Correct? Any pet owners here or any in this call? No, I had a pet once, predominantly a dog. The agent here is the dog, okay? The dog or the pet that you have. The environment is the world, your park, your house, everything that you have. Reward is you give them treats, either small form of chocolate or small form of, let's say, candy, whatever that pet likes. And then you try to inculcate behaviors. Hey, not to bark, sit down, don't go there, and stay here. And whenever they do, you give them that treat. That is what reinforcement learning is. If I do something, I get rewarded. Rewarded. And this. Yes, Aditya.
So this environment can be simulated and like natural,
Yes,
both
it can
or
both. Example, guinea pigs that scientists predominantly use for, let's say, drug testing, everything else. Those environments are simulated. They try to inculcate behavior in terms of how you react to various kind of dopamines, how you can react to various kind of threats. All of these, all of these environments are simulated. So this is the world. World can be, you can have a simulated environment, you can have a real world environment. It can be anything. It can be how they behave in your house, in the park, or let's say in a cage, or in a public setting. It can be anything. Environment is the definition of whatever you have used in agents environment. So it's open per se. Okay. Then and the key idea is very simple: learn by trial and error, and balance exploration and exploitation. We'll learn a little bit about it more. So learn by trial and error. Your dog will bark a couple of times. You will shout out at it. And when it does, you will pat him and then give the reward. Sometimes it will not shout or it will shout, let's say, shut up very easily. Then you will give the reward earlier. The idea is to learn by trial and error. That is what RL is in a nutshell. So what are the core components of an RL? Predominantly based upon an agentic environment per se. First is the agent, which is the sole decision maker here. Okay, you are reinforcing a behavior. You're not making that decision. The agent still makes that decision. It can be anything. A game that Google released. Actually, OpenAI released some time back, which won in Dota, or self-driving car that we are creating. These guys will make that decision. Okay, the environment here is the world that agent interacts with. Self-driving will interact with the roads. Game playing AI will interact with the game board or the game setting. State, which is the current situation. What is the car situation? What is the game score? Or what are the enemies positions? Action is possible moves. You can, for a car, you can accelerate, brake, turn, and those things. And similarly, in a game, attack, defend, buy some things, all those action that you can take. What is the feedback loop? And if you see there is there are some variables assigned to it. State is S, action is A, reward is R, and they have these acronyms. And the feedback is if you drive safely, you reach from A to B, you get +1. If you don't reach from A to B without crashing, you get -1. And similarly, in a game, leaderboard can be you move up in a leaderboard. Those kind of reward system that you can design for your agentic system. Then there is the policy. It is a strategy that is infused, which helps to choose action based upon states. This is where the tuning comes in per se in the picture. Okay. Then there is value function. This is the expected cumulative reward from a state. If you're in a state and you take an action, what is the value function? What will I get out of this? Example, if I attack this, I'll get opponent's coins. If I, let's say, take a highway versus take a underpass, highway I might reach faster. So I might go from one to A point to B point faster. So I'll save the TAT per se and then I'll be rewarded for it. Then there is Q value function. Q value function is expected cumulative reward for taking an action in a state. Value is this is what will happen. Q value is if you take that action, what is the expected cumulative action for particular action that you're going to take. That is how those are the core components of any RL algorithm. We learn a brief about few of them. What are the types of reinforcement learnings algorithms? First is actually a dynamic programming. These methods require a complete model of the environment, complete, and are used for planning and evaluation of policies. Example, if you're creating a self-driving car, there's a high chance that you'll prefer a complete model of the environment, whatever is possible, wherever you are, at least in the scope of city that you are in. Your model knows all the map, your model knows all the behavioral pattern, all those kind of things that you'll optimize for. For game, that may not be true. Then there is Monte Carlo method. These rely on sampling and are used when an agent can explore its environment multiple times to gather information about states and reward. Monte Carlo, imagine you have created a dynamic programming environment and you have self-driving car for entire planet Earth. Imagine, okay? Now you have to go to Mars. We succeed to do that. There are no roads, you know, and you still want to create a nominal path. Monte Carlo method will say, कि, hey, go to 100 meter, see what happens, come back, and then decide what is the next step. How rovers are configured predominantly. The rovers predominantly work in a Monte Carlo method. There is the environment, you don't know what will happen, and you can explore a lot of alternatives before deciding and collect a lot of samples in terms of and then decide what is the right state and have a right model of the state, and then rewards can be tweaked. Hey, if you go 200 meters without jamming into a rock, let's say you get rewarded something, and then similarly if you go uh, let's say 5 feet deep and come out, let's say in 2 minutes, you're rewarded. So these can be tweaked. Then there is temporal difference learning. This combines the idea of dynamic programming and Monte Carlo. Predominantly, these are used in very complex agents. Uh, the agents that we currently see don't have this actually. This allows agent to learn completely in an incomplete information of the model, which is very difficult. So agent has some information and it is able to marry it with Monte Carlo and then decide what are the right rewards, what are the right behaviors. This is the third layer. So what are the challenges in RL? As I said, first is exploration versus exploitation. Okay, and this is one of the core theme of RL. Whenever you hear on hear about RL or any form of RL that a lot of these guys are working on, you'll see them talking about, hey, how much are you exploring, how much you are exploiting. Because one of the fundamental challenges RL is balancing exploration. How much do you, let's say, simply explore? Try and different actions, and then exploitation, and choosing known action that yields high reward, which is I know if I'm a car, always take highway, it doesn't matter. So, example, always take the highway because for some reason you don't need to, let's say, wander around in the city to find the best path. Maximum probability is you will reach from A to B in at least in the top n times from highway. So you'll always go on highway. So if everybody does that, that will soon start to not be true. This is how you define. Instead of example, when we drive, let's say, forget about manual drive, agentic driving. When we drive and we use maps, we do take these shortcuts, right? Those are exploration paths. हे यहाँ से चल के देख लेते हैं, शायद जल्दी पहुंच जाए, गूगल एक ऑल्टरनेट दिखा रहा है वर्सेस हाँ ये पता है यहाँ से यहाँ चलना है. So it's the balance between this, कि how much you are going to try and how much you're going to simply choose the path that you already know works, is key to any reinforcement learning model. Then there are delayed rewards, which is in many RL scenarios, rewards are not necessarily immediately given. This delayed feedback complicates learning. An agent must infer which action lead to positive outcomes over a longer time frame. Any example that comes to your mind whenever you see a reward later? Example, easy example is DALI. DALI has an N set of algorithm and they release these models. And you understand? A lot of these guys release newer version of models. Those agents will learn the feedback based upon whatever people are doing for a, let's say, 2 month period, 3 month period, 4 month period. Then only they're going to decide, hey, whatever we did was right or not. They cannot say, hey, the output was there and people are happy. No, people might comment, hey, these are not right set of images that we're looking for, or this is not the right set of prompt that output that you're giving. This is not the necessary depth that you are giving. And rewards can be delayed as big as people, let's say, buying for that agent's information after 6 months, after a year. So those kind of delayed rewards are really challenging for any RL algorithm. This is a very crud example. Then there is partial observability. Hope exploration versus exploitation is clear. Delayed rewards are also clear. Then there is partial observability. In real world application, agent often operates in an environment where they cannot fully observe the current state. It's absolutely uh, true. Example, if you're actually we have already learned about various kind of environments. If the environment is partially observable, to create a RL algorithm and making sure that it sticks is really difficult, because this necessitates techniques such as belief state. कि हाँ, I believe this is true. State can be anything, but you have to believe something ki true. Everybody will not. If I'm going to take left, everybody is also going not going to. Anybody is not going to override the signal. That is a belief. That is the belief that we have. Hey, this is how I'm going to write. People can override it, or memory based approach to maintain understanding of the environment. These are challenges. You will have partial states or belief states. You may have rewards which are very delayed. You get to know if whatever algorithm that you have decided works or not after 6 months, 4 months. And then there is how much do you explore, or how much you choose between, hey, this is, I know what works, always stick to it. These are the primary challenges in any RL algorithm. Then there are few applications of RL. Some easy one to think of is first is robotics. A training to a robot that people have already shipped to perform tasks through interaction with the physical environment. You train them. You have seen this videos predominantly or various factories that we have. कि, hey, uh, always pick an item which is, let's say, 5 feet away, and drop them at 3 feet away. You configure them. The first is called as fine tuning. Then when they're agentic, you can train them. And if you train them, if you move the object a little behind, it will calculate the minus, plus or minus delta and do the same action. Okay. So this is what a reinforcement training can be in robotics. Then there are game playing. AlphaGo was very famous. Uh, and then there was a DeepMind which started in chess. And then in finance, we have lot of agents actually which learn trading strategies by optimizing long-term return based upon market condition. People already have these algorithms. It's just that they're not agentic in nature as of today. People are still working on it. Okay, hey, they can be agentic. They can make these decisions. So they have static trading algorithms which they have learned from, let's say, a century. Now they are becoming agentic, which is how do I optimize and give them the freedom of, if you remember, there was a Q value and there was a value function. If you configure it right, it will optimize for that delta. Hey, you might have heard of alpha and beta in the market. Those can be your rewards for your finance agent, and then you can define how much alpha that you're gunning for. An agent will might take those free decisions. Okay, if the market is dip, do you hold, or you do you aggressively do short trades? This is kind of freedom agent will have versus a static algorithm it will have. There are a lot of applications in these areas. Now let's learn basics of more than few algorithms which are very famous. First is Q learning. We already know what is Q value, correct? Which is this represents the expected future state of rewards based upon what is the action that you're going to take in a state. Then you also have exploration versus exploitation. In Q learning, you predominantly use a greedy strategy to balance new learning and leveraging known rewards. So you see, कि, hey, if this new learning is working, switch to it. If it is not working, switch back to the previous one. So this is what a very simple Q learning is. Nothing special. In deep QN is basically an extension of Q learning. This utilizes a deep neural network. We learned that in session 2 of this to approximate what is the key value for complex environment. So Q learning basics are whatever agent that we are going to create in simple agents. It is applicable, which is use a greedy strategy, choose a new action, see if it is working. If it is not working, switch back immediately to the what was working, and then after some time try a new action. Then after some time try a new action. For deep QN, it is working on a very large compute system having a neural network to approximate previously what are the various Q values which we're going to have based upon a complex environment. That is a deep QN. Then there is policy gradient method. Policy gradient method is basically an RL algorithm that directly optimizes the policy, which is a mapping of state and action. You imagine this being one of the famous strategy patterns that sort of we used to have. So this is actually a strategy pattern. Technically, you have a state and you have a set of actions, and you have all the possible um, Q value outcomes available to you. Correct. And unlike value-based system, which derives policy from a value function, policy gradient method focus on adjusting the policy parameter to maximize expected returns. This means imagine these policies of hey, being aggressive with five people. I'm imagining a football agent. Okay, let's take that as an example. Both two agents are playing football, and there are various strategies that you can use. Being aggressive with four people, being aggressive with three people, being aggressive with 10 people, and based upon current state, it can optimize the value of who are you going to choose these three people, how much aggressive that they're going to be based upon the maximum expected returns. This is how you're going to create this gradient of various policies for you to choose from. So this is what a policy gradient method in RL means. There are a lot of advantages. Very simple is this is a direct optimization. What works for me, I need if I'm losing, I need the next quarter. Let's maximize for that. Switch two people, get the best two attackers in, and then let's go on attack. That is what you are directly optimizing for a immediate outcome. It is flexible. It is not necessary in terms of it can incorporate domain knowledge. The person who's doing this needs to have those domain knowledge. Okay, what works, what might not work, for you to apply them. And then there is convergence. Uh, it is trying to optimize for local optimum. In next 20 minutes, we need that goal. Okay, because the time is going to go away. So we need that goal in next 20 minutes. So imagine that is for a football agent. Imagine for a ambulance service. Let's say you're creating an agent for an ambulance service. It will take a lot of actions in terms of hey, uh, if the patient is very critical, the policy would be leverage network to let's say get few roads open so that you can go on top, which might be of highest traffic, and others can stay as is. Those kind of dynamic decision it can make to guarantee the local optimum, which is next 10 minutes we have to reach the hospital. Then there are a lot of challenges because if you understood whatever I was saying, there is a lot of high variance, a lot of decision making is happening at runtime. So there is a lot of estimated grades which will change, can have variance, and this can also slow down conversions. We'll try to learn this when we go deeper. And then there is sample inefficiency because you're making dynamic decisions. You don't know what will actually work or not work, and this will require either previous knowledge or model which has this information or sampling, a lot of sampling to be done. Okay, to be done. A football game might be of 90 minutes. Imagine an AI agent which is being optimized will use multiple years to be trained because it is going to learn a lot of different policies, but creating a lot of sampling. Last is contextual bandwidth. Bandit, sorry. Now, name is fancy. Name is fancy. This is a subset of RL. This integrates contextual information into decision making process. Okay. If I go back, this was simply action pair and optimizing a greedy strategy, Q learning. Deep QN is basically on doing that on a good neural network. Policy gradient basically is, to simplify form, is a very strategy pattern where you're updating policies to optimize the maximum output. Contextual bandwidth is a subset. They represent the middle ground between traditional multi-arm bandwidth problems and RL. Let's go in simple definition, which is key characteristics are you have an immediate reward. Contextual bandwidths provide instant feedback for every action taken. Example, if you remember, one of the challenges was rewards can be delayed, but you can get feedback. Contextual bandwidth ensures that you get feedback immediately, allowing for a very quicker learning time compared to a delayed reward in a full RL. Okay, you ensure that you will get feedback immediately. Then it is single step decision making. Unlike 4RL, where action can influence future states, contextual bandit operates under the assumption that each action outcome does not affect subsequent state. Example, if you're driving something and you choose an action of taking left, you're in a different position in a environment, and versus, and now your next set of action will be based on what is the traffic in front of you or what are the paths in front of you. In context, single step decision making process of contextual bandwidth, it is imagining if you are here, if you take a left turn, what will happen. This is the reinforcement learning that you'll have. It is not going to go there per se. Okay, because it is taking that contextual information of these are the end paths. You can take this, and you don't have to actually go there for then decide what needs to be taken. And if you remember in previous, we are going there and then coming back if that didn't work out. Here, that's not the case. You will get all the options, single step decision making, because you'll take that turn and you'll have that as an information. Then it trains ki based upon whatever state changes happen, it takes that into account if this step was right or not. When we are driving, we take the left turn, we have to come back entire circle to reach there, right? That's not the case. It gives you, okay, hey, if you turn back, this is what is the reward which will you get. And you have good amount of contextual information which has to be there. Imagine, in order to make this kind of agent, you need to have mapping of every single car which is out there, every single decision that they can take, and then you can create this let's say contextual bandit RL algorithm. So if I take left, what will happen? A lot of contextual information has to go in. Cool. So a lot of lot of talk per se till now. We learned the basics of it. I'll revise predominantly the algorithm so that they are deeply ingrained, and we'll go in mathematical detail in the next session. Q learning, if you remember, what are the key actions? These are the components of an RL. First is an agent. Agent has an environment. Agent has a state. Environment, in you have a state. You can take an action. You will get reward based upon an action. There is a policy based upon which you can choose an action. And then there is a value function, which is an expected output or reward from a state. And there is the Q value, which is expected cumulative reward for taking an action in that state. These are the core components for algorithms, which is Q learning basis is simply a greedy strategy. Hey, let's try a new thing. If they work, amazing. If they don't, let's stick to what we know. Deep Q&A is basically let's do that on a very large neural network so that we know all the future possible Q values also. This is basically going deeper. Uh, Policy gradient is basically a strategy pattern. Imagine, and you are tweaking the policy to maximize returns. Okay. Then contextual bandwidth is you're actually not taking these actions. Technically, your single step feedback, and there is no direct relation of an action in a future state. If you're in a state, if you take an action, contextual bandwidth ensures that contextually it is the right decision. It doesn't matter what will happen to the state based upon that action. This is the difference between these the algorithm that we'll deep dive in the next. Any questions till now? That's it. That's it for today's session. What do you guys?
Anupam, like till now we used to discuss peas. So from now onwards, जो आपने you added three more functions which were policy, reward, and there was another thing, value function and Q value function. So does the paradigm shift now? Like P's are
No,
no longer.
not technically actually. Ps will always be true for every single agent. This is predominantly in order to create that agent, what is the algorithm that you have chosen to, let's say, to reinforce these learning. And whenever you do that, apart from Ps, you have more let's say fine-grained items to be taken care of. And
Got
these
it. So
all
this
of
is
these are
one level
important because
below.
all of these are actually algorithmic inputs that we'll learn in our next session.
Okay. And the most uh, complex model we had learned till now was utility-based model. But
Yes.
in utility-based model also, the utility functions were predefined, at least from our examples, what we learned about. So here, the difference is you don't even know if this action can cause this reward and is this cumulatively the best. That is what
You don't know.
RL is trying to solve.
Yes. Yes. And this obviously RL will be for a larger, bigger problem. It will not be for a simplified utility agents. We are moving upper per se in our complexity of agents. Somebody who writes code for you, it's a bigger agent. Somebody who takes this AI classes will be amazing agent. Okay. For imagine we are moving up in complexity. If this information will work or not, if you learn the concept or not, those are the gray areas. Let's say for a AI session taker. They will only know when the session is over. You give those feedbacks. Understand? But if I was a utility agent, I'll simply give it an input. Hey, this is my preview. Just create the slides. Let's talk about it for 30 minutes. It will not optimize if the sessions are good, if your solutions are feedback, you guys are learning. That's the difference. It will optimize for if you simply give, it might optimize for everybody should give. If everybody gives you feedback in, let's say, every single minute, 5 minutes, and gives you feedback after a session, it will optimize for, hey, and that is the utility point for you. If everybody gives you an aggregate 4 rating, you get +1. If everybody doesn't, -1, let's say, based upon number of people. It will optimize for tone, pace, based upon that. But RL will optimize for you if you're learning deeply or not, you're solving for assignments or not, are you able to build your agents or not. So RL will go much, much deeper. Hence, it will take a lot of action which are not known uh, if they will stick or not.
These three new things I think add to the complexity of it, which is value function, Q value function.
And pause.
They are like heuristic and the policy, like which policy is as you put it, it's like the strategy, what
Yes.
to choose at what point.
Cool. Some simple example are this to make it relatable. Imagine if you have to create a self-driving car. Self-driving car. So what will be the best algorithm? We know three. Q value, we know contextual bandwidth, and we know policy gradient. Okay. If remember those few difference, I'll repeat them. Simply state action pair, choose the greedy algorithm. This is tweak the policies and create that gradient for you to maximum return. Contextual bandwidth is don't worry about if the action will change the state. Just take that action and get that immediate feedback. Um, if you're training a car, best will be a very deep QN to learn optimal driving strategies. And there are a lot of tools. We'll learn about them in next session. An example, if you're going to state is car position, speed traffic condition, action is accelerate, brake, steer left, right. Reward is +1 for straight driving, -100 for collisions. Correct. And so deep QN, which is understanding outcome, understanding the what are the best state of action, being greedy, but knowing all the possible outcomes, everything. If 10 people are in front of me, the one person is left on me, who do I crash into? All those complex moral discussion will happen that can only be solved with a very deep neural network. Okay, so you will prefer to use a self-driving car, a deep QN. Say for robotics, a simple problem is train a robot to pick and place objects. State is their joint angle, their object position. Action is move the joints, grip or release the object. These are simple. +1 for successful placement, -1 for dropping an object. Here, policy gradient method can optimize simply basic. If the item is very difficult, move, see those gradients. Because you don't need a very deep neural network to train this problem system that you're going to solve for robotics. If you're going to do something like what Boston Dynamics is, which is a very fully functional humanoid, then maybe policy gradient might not work. You would prefer a deep QN in that case. Then this is personalized recommendation, which is your ad engine. You need for very hyper personalized recommendation engine. An engine needs to do that, which is recommend products to user to maximize engagement. A very traditional B2C use case. States our user browsing history preference. I don't know. We'll not be comfortable giving our browsing history and then your preferences. And then action is to recommend a project. +1 if they click it. +10 for a purchase. This is the agent that you're creating. Your contextual bandwidth might be very good. You don't need them to go very deeper, correct? Don't need them, those users to try various products and go. You just simply put one product in front of them, see if they work. It doesn't work, put another product. That is how we optimize. That's how, because it is taking a single step optimization. It is giving one single recommendation to the user and then it is optimizing. So this the contextual bandwidth will fit the best here. You don't need a very deep neural network. Same we did at UC. We didn't use a very deep neural network to build our recommendation engine. A very pure mathematic function. We used to judge it based upon if there is a conversion update, and we tried a lot of strategy based upon your age. Very simple. Hey, if the guy is in between 27 to 28, just say give them the top product to be massage. The guy is above 35, give them the top product being let's say haircut. Those are kind of simple strategies that we used to use, and that is what a contextual bandwidth is predominantly. Cool. So I hope this three algorithms are relatable now a little bit. We'll deep dive a lot purely in mathematics. Next session will be entirely math based. Be ready. Do revise these simple definitions so that it is easier to grasp. That's it from my side. We have 3 minutes. But if you guys have any questions.
And can we discuss on Q value and value functions basically? So like the main difference between both is one is you get reward after a state is achieved, and in in Q value we have a reward whenever we're in current state and we take an action basically. So there are two kinds of rewards. One is before, after taking action, and one is after achieving something.
Correct.
Right?
So imagine you change your state, and you change your state. You might take n number of actions to reach to that. This is a community reward of all of that. Q function is a subset of it, which is when you take an action, what are the n set of reward that you get for taking that action? Imagine, let's say you're driving a car, you change the state of the change state is your car was standing, now car is moving. Okay, until the car moves. This is the cumulative reward of, and it reaches the next state, which is it has stopped. It has stopped. All the rewards will come in under value function. Once you are, but once you take and when the car is moving and then you take a left, if there is a reward for that, or let's say you save some time, then that is q value.
Okay.
So Q value is value function plus something else. Like
No, no.
additive work,
Value
if you
is
take an action, what would happen?
uh, Based upon my current understanding, q value sounds like a subset of what you can have in a value function. Value function can be a derived state on various q values. Example, you start another example in a game, your state was your character has not started to attack. Now you started to attack, correct? That immediate action or value that you will get by attacking the first opponent is can be a q value function. But in the state of attacking, and you do that, let's say till you win the game, all those n number of actions, all the absolute value of all of those combined will become your value function. What is the value of attacking versus what is the value of attacking now to, let's say, Saurav? Q value function is what is the value of attacking, let's say Aditya, Saurav, uh, Yugang and Anish independently. Value function is what is the value of attacking. It can be of all of you combined or two of you combined, based upon what is optimum for me to win.
Can
Okay,
it be thought of like similar to a graph problem where edges are actions and then the nodes are states? So edges also have some way like rewards and
same
then
rewards. Yes. 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 And the Q value is, let's say, from going from one state to another. What is the reward of the arrow per se when you are traveling from one node to
yeah,
another?
yeah.
Cool, guys. I guess that's it. Thanks for tuning in. Let's meet next week for a lot of mathematics. Cool. Take care. Have a good weekend.